When a fighter jet takes off, you sometimes see a sudden burst of flame shooting out of the back. That's the afterburner. It produces enormous thrust and burns an enormous amount of fuel. In fact, it's one of the least efficient ways to power an aircraft. So why would engineers design something that wastes fuel on purpose? In most machines, efficiency is everything. Cars are designed to use less fuel. Airliners are built to travel thousands of miles as economically as possible. So adding a system that dramatically increases fuel consumption sounds like bad engineering, especially on an aircraft where every drop of fuel matters. So if afterburners are so inefficient, what problem are they solving? To understand afterburners, you first have to understand how a jet engine normally works. A jet engine pulls in air from the front. That air is compressed, mixed with fuel, and ignited. The explosion pushes hot gases out the back at high speed. And according to physics, pushing air backward pushes the aircraft forward. The more air you move and the faster you move it, the more thrust you create. But even after this process, something surprising remains. Even after combustion inside the engine, not all the oxygen in the air has been used. There's still leftover oxygen rushing out the back with the exhaust. The afterburner takes advantage of that. It injects additional fuel directly into the hot exhaust stream and ignites it. That creates a second burst of combustion outside the main engine core. The result? A massive increase in thrust. It's like adding a temporary rocket boost to an already powerful engine. But that extra power comes at a cost. The reason afterburners burn so much fuel is surprisingly simple. They skip efficiency. In the main engine, fuel is carefully mixed and compressed to extract as much energy as possible. But in the afterburner, fuel is sprayed into the exhaust without additional compression. That means a lot of fuel is burned just to create a rapid expansion of hot gases. It produces enormous thrust, but far less efficiently. In fact, a fighter jet using afterburner can consume fuel several times faster than in normal flight. It's raw power over efficiency. Because afterburners consume fuel so quickly, pilots don't use them all the time. They're reserved for critical moments. During takeoff from short runways, when climbing rapidly to high altitude, or in combat when acceleration can mean survival. Afterburners also allow some jets to break the sound barrier. They aren't designed for long-distance cruising. They're designed for short bursts of overwhelming power. So afterburners aren't a design flaw. They're a deliberate trade-off. In aviation, efficiency matters. But in combat, power matters more. The ability to accelerate instantly, to climb faster, or to outrun a threat can make all the difference. It's a reminder that in engineering, the best solution is always the most efficient. Sometimes and if you enjoy uncovering the hidden logic behind advanced machines, subscribe for more simple things with surprising stories. And afterburners aren't the only systems built for moments of extreme demand. All around us, machines are designed with hidden reserves, power that stays quiet until it's absolutely necessary. Once you start noticing that, even a flash of flame in the sky tells a much bigger story.